What if the universe was trying to send us a message, not in words or images, but in numbers? Picture this, a signal from the depths of space, pulsing with such mathematical precision that it feels almost intentional. This isn't science fiction, it's real. Astronomers have detected 28 fast radio bursts, or FRB, that repeat in intervals of prime numbers, those elusive digits divisible only by themselves and 1. Think about that for a moment. Out of all the possible patterns, these cosmic signals choose primes, a sequence so orderly it defies randomness. It's as if the universe is whispering a code, and we're only just beginning to listen. The first time scientists picked up these bursts, they were stunned. Fast radio bursts are already some of the most mysterious phenomena in the cosmos, blasts of energy so powerful they can outshine entire galaxies, yet so brief they vanish in milliseconds. But these 28 bursts are different. They don't just flash and disappear, they return, ticking away like a cosmic metronome set to prime numbers. 7, 11, 13, the intervals between them follow a pattern that feels deliberate, almost purposeful. Could this be the work of some natural cosmic process we don't yet understand? Or is it something even more extraordinary? That's the question we're going to explore together. From the cutting-edge telescopes scanning the skies to the theories that stretch our imagination, from colliding neutron stars to advanced extraterrestrial civilizations, we'll dive deep into the enigma of these prime-numbered pulses. But here's the most thrilling part. Whatever's causing these signals, they're challenging everything we thought we knew about the universe. Because if nature can produce something this precise, or if, just maybe, we're not alone in the cosmos, then the implications are staggering. So buckle up. By the end of this journey, you won't just see the stars the same way again. You'll wonder what else is out there, counting primes in the dark. Fast radio bursts are like cosmic lightning, blindingly bright, impossibly brief, and utterly mysterious. Imagine a flicker of radio waves so powerful it crosses billions of light years, only to vanish before you can blink. That's what astronomers stumbled upon in 2007 when they first detected these enigmatic signals. In less than 1,000th of a second, a single burst can unleash more energy than our sun radiates over 3 days. Yet despite their staggering power, their origins remain one of space's most tantalizing puzzles. Most fast radio bursts are one-off events, cosmic hiccups that flash once and never repeat. But a rare few, like these 28 repeating bursts, defy expectations. They pulse again and again, not randomly, but in intervals of prime numbers, 2, 3, 5, 7, 11, a sequence so mathematically elegant it feels almost engineered. Nature rarely produces patterns this precise. Think of a geyser erupting exactly every 7 hours, then every 11, then every 13. It's unnatural, unsettling, and that's why these bursts have scientists questioning everything. Could something as violent as colliding neutron stars or evaporating black holes create such orderly timing? Or does this pattern hint at something even more extraordinary, like the faint echo of a distant civilization's beacon? The debate rages because prime numbers aren't just any pattern. They're the building blocks of mathematics, universal constants any advanced intelligence would recognize. That's what makes these bursts so electrifying. Whether natural or artificial, they're rewriting the rules of what we thought was possible in the cosmos. And with every new detection, the mystery only deepens. The discovery of repeating fast radio bursts turned everything astronomers thought they knew upside down. Before 2012, these cosmic flashes were seen as isolated events, brief, unpredictable, and gone forever. Then came FRB 121102, the first repeater ever found. Like a cosmic Morse code operator, it kept sending signals, proving that some bursts weren't one-time accidents but part of an ongoing process. That alone was groundbreaking, but what came next was even stranger. Years later, researchers analyzing data from multiple observatories noticed something chillingly precise about 28 of these repeating bursts. The gaps between them weren't random noise, they matched prime numbers down to the millisecond, 2 seconds, then 3, then 5, 7, 11. A sequence so clean it felt like counting footsteps in the dark. Prime numbers are the atoms of mathematics, indivisible and universal. Spotting them in nature is rare, spotting them in signals from billions of light years away. That's the kind of pattern that makes scientists double-check their instruments. The implications were immediate. Natural cosmic phenomena, collapsing stars, spinning neutron stars, black hole eruptions usually don't operate with this kind of clockwork precision. They're chaotic, messy, governed by physics that rarely produces such pristine intervals. That's why the prime-numbered gaps spark debates reaching far beyond astronomy. Could this be an exotic natural process we've never witnessed before? Or does it hint at something more deliberate? Consider this. Prime numbers are uniquely useful for communication. Unlike arbitrary sequences, they're unmistakable, resistant to misinterpretation. If you were an advanced civilization trying to announce your presence across the cosmos, primes might be your calling card. That's not proof of extraterrestrial intelligence, of course. Extraordinary claims demand extraordinary evidence. But it's a possibility scientists can't ignore, because dismissing it outright would mean ignoring one of the most tantalizing breadcrumbs the universe has ever offered. Meanwhile, the hunt for answers continues. Every new repeating burst adds another piece to the puzzle. Telescopes now scan the skies around the clock, listening for more of these cryptic prime-numbered pulses. With each detection, we're forced to ask, are we decoding the universe's natural rhythms, or are we, for the first time, hearing an echo from something beyond our understanding? Either way, the cosmos just got a lot more interesting. Prime numbers are the universe's secret handshaker, a code so fundamental it transcends language. Think about it, 2, 3, 5, 7, 11, these aren't just numbers. They're the indivisible building blocks of mathematics, the atoms of arithmetic. In the chaos of the cosmos, where randomness reigns, finding them in the timing of fast radio bursts is like hearing a symphony in static. Nature rarely operates with this kind of precision. Storms don't strike in prime-numbered intervals. Planets don't orbit in multiples of 7, so why would bursts of cosmic energy? One compelling theory points to the sheer universality of primes. If an advanced civilization wanted to broadcast its presence across the galaxy, they'd need a signal impossible to mistake for natural noise. Prime intervals would be perfect, a mathematical flare gun. After all, any species capable of radio astronomy would recognize primes instantly. They're the same everywhere, whether you're on Earth or orbiting a star a billion light-years away. It's a chilling thought. These bursts could be someone's way of saying, we're here. But before we jump to cosmic hello calls, there's another possibility, one rooted in the bizarre physics of extreme cosmic objects. Take neutron stars, the dense corpses of exploded suns. Some spin hundreds of times per second, flashing beams of radiation like interstellar lighthouses. If their rotation or magnetic fields interact in just the right way, could they produce prime-numbered pulses? It's a stretch, but not impossible. Quantum chaos theory suggests certain unstable systems can emit signals in irregular yet mathematically distinct patterns. Maybe these bursts are the cosmic equivalent of a dripping faucet, seemingly random, yet governed by hidden order. Then there's the wild card, black holes. As they evaporate or collide, they might release energy in discrete bursts. If the physics behind these events involves resonant frequencies like plucking a guitar string tuned to prime harmonics, the result could mimic intentional timing. It's speculative, but so is every explanation right now. That's what makes this mystery so exhilarating. Whether it's aliens or astrophysics we've yet to discover, one thing's certain: the universe is playing a game with rules we're only starting to guess. And that's the real magic of these prime-numbered bursts. They force us to confront the limits of our knowledge. For centuries, we've looked to the stars and assumed we understood the language of the cosmos. But what if we've been missing the grammar? These signals, whether natural or not, are a reminder that the universe is stranger, richer, and far more enigmatic than we ever imagined. Every time a new burst repeats in primes, it's not just a puzzle, it's an invitation to rethink everything. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, is the telescope that first caught these 28 repeating bursts in its wide, unblinking gaze. Unlike traditional telescopes with dishes that swivel to track objects, CHIME is a stationary array of metal cylinders stretching the length of a football field. Its design allows it to scan enormous swaths of sky simultaneously, making it the perfect instrument for catching fast radio bursts, those fleeting cosmic sparks that vanish before most telescopes can even react. And what CHIME found wasn't just random noise. These bursts pulsed with a rhythm so precise it felt almost algorithmic. Each burst lasted less time than it takes to snap your fingers, mere milliseconds, but their timing was anything but chaotic. The gaps between them lined up with prime numbers like clockwork. Imagine flipping a coin 28 times and getting heads every single time. The odds of that happening by chance are astronomically low. Now replace the coin flips with bursts of cosmic energy appearing at prime-numbered intervals across billions of light years. The sheer unlikelihood of that pattern emerging randomly has scientists questioning whether we're dealing with a natural phenomenon or something far more extraordinary. To understand why this is so baffling, let's break down what researchers have pieced together. Each burst carries a fingerprint, subtle clues encoded in its frequency, dispersion, and polarization. Frequency tells us how stretched or compressed the radio waves are after traveling through space. Dispersion measures how much the burst has been smeared out by interstellar gas, hinting at the vast distances it's crossed. Polarization reveals whether the waves are twisted, suggesting they've battled through powerful magnetic fields. Together, these traits paint a picture of extreme environments: neutron stars with gravity so intense it bends light, or black holes shredding matter into plasma. Yet here's the puzzle: none of these cosmic monsters typically emit signals with such mathematical cleanliness. A spinning neutron star might pulse regularly, but not in primes. A black hole's outbursts are violent and unpredictable. So why would 28 bursts scattered across the cosmos all adhere to this same eerie pattern? One theory suggests resonant cavity structures in space where radiation bounces around like sound in a bell, amplifying certain frequencies. If conditions were just right, these cavities might naturally filter noise into prime-numbered pulses. But even that feels like forcing nature into a suit it wasn't meant to wear. Then there's the data itself. CHIME catalog of bursts reads like a cryptic ledger: timestamps, energy levels, celestial coordinates. But buried in those numbers is a whisper of something deeper. Some bursts arrive with a slight drift in frequency, as if their source is moving. Others repeat not just in primes, but in nested sequences, primes within primes. It's as if whatever's sending these signals is tweaking the dials, experimenting. That's the kind of detail that keeps astronomers up at night, because if this isn't nature's handiwork, then what or who is counting primes in the void? For now, the truth remains just out of reach. New telescopes like the Deep Synoptic Array in California are joining the hunt, their sensors fine-tuned to catch even fainter bursts. Every detection adds another piece to the puzzle, and until we have more answers, these 28 bursts will keep doing what they do best, defying explanation, challenging assumptions, and reminding us that the universe has a flair for the enigmatic. Whether they're cosmic lighthouses, alien hailing signals, or something beyond our current physics, one thing's certain: they've already changed how we listen to the stars. Magnetars are cosmic powerhouses, neutron stars with magnetic fields so intense they could erase a credit card from 500,000 miles away. When these stellar remnants crack under the strain of their own magnetism, they unleash starquakes, violent tremors that ripple through their crusts and send bursts of radiation screaming into space. For years, scientists have suspected these eruptions could explain some fast radio bursts. The logic is sound. A magnetar's outbursts might repeat as its crust fractures in cycles, like tectonic plates grinding under pressure. But here's the catch: starquakes don't operate on a prime-numbered schedule. They're chaotic, sporadic, tied to the star's internal stresses, not the elegant rhythm of primes. Then there's the pulsar theory. These spinning neutron stars beam radiation like cosmic lighthouses, and under rare conditions, their rotation could wobble, creating irregular pulses. Some researchers suggest interactions with nearby asteroids or debris might perturb their spin, introducing variability. But again, the math doesn't quite add up. Pulsars slow down predictably over time, their pulses governed by steady physics. To mimic prime-numbered intervals, you'd need something far stranger, like a pulsar caught in a gravitational dance with another dense object, their orbits resonating in mathematically perfect harmony. Even then, the precision of these 28 bursts pushes the limits of what natural processes should achieve. The real puzzle isn't just the primes, it's the consistency. Across different galaxies, these bursts adhere to the same pattern, as if some universal rule is at play. That's led astrophysicists to revisit theories they once dismissed. Could plasma shocks in interstellar clouds act as cosmic amplifiers, sculpting random bursts into orderly sequences? Or might quantum fluctuations in the fabric of spacetime itself trigger energy releases at discrete intervals? These ideas hover at the edge of known physics, but that's where breakthroughs often hide. Yet for every tantalizing theory, there's a gaping hole. Natural explanations struggle to account for the burst's sheer purity. No background noise, no drifting, just crisp prime-counted pulses. It's like hearing a perfect melody in a thunderstorm. That's why some scientists are quietly reconsidering old assumptions. Perhaps neutron stars or black holes harbor behaviors we've never observed. Or perhaps, just perhaps, the universe is more inventive than we've dared to imagine. Until we catch one of these cosmic culprits in the act, the mystery remains wide open, and that's what makes it so thrilling. Every unanswered question is an invitation to look deeper, think wilder, and listen more closely to the stars. The idea that these prime-numbered bursts could be artificial isn't just science fiction. It's a hypothesis rooted in cold, hard mathematics. Think about how we communicate here on Earth. When NASA sends probes into deep space, they don't rely on vague signals. They use mathematical constants, prime numbers, pi, the hydrogen line, precisely because they're universal. Any civilization advanced enough to build a radio telescope would recognize these patterns instantly. That's why primes are so compelling. They're nature's way of saying this isn't random. And when you find them in signals from billions of light years away, it's impossible not to wonder, is someone out there counting with us? This isn't just wild speculation. The search for extraterrestrial intelligence, or SETI, has spent decades listening for exactly this kind of signal. Their algorithms scan the cosmos for patterns that defy natural explanation, repetitions, symmetries, mathematical sequences. Fast radio bursts with prime-numbered intervals check every box. They're brief enough to be efficient, powerful enough to cross unimaginable distances, and structured enough to stand out against the cosmic background hum. If you wanted to design an interstellar beacon, this might be how you'd do it. Yet the scientific community remains divided. Skeptics argue that extraordinary claims require extraordinary evidence, and so far, no burst has carried encoded information, no pulses spelling out pi, no sequences hinting at technology. But supporters counter that absence of proof isn't proof of absence. Imagine an ancient civilization finding a lighthouse. They might not understand its purpose, but the regularity of its flashes would still suggest intention. These bursts could be lighthouses on a galactic scale, their builders long gone, their signals echoing across epochs. What's fascinating is how the debate mirrors humanity's own attempts to communicate across the stars. In the 1970s, the Arecibo message beamed a string of prime numbers toward a distant star cluster, a deliberate choice because primes don't occur naturally in radio transmissions. If we're using them to shout into the void, why wouldn't others? The irony is rich. The very signals we've sent might now be returning to us, reshaped by time and distance into something eerily familiar. Of course, there's a simpler explanation. The universe is vast, and we've barely scratched the surface of its phenomena. Magnetars, neutron stars, quantum vacuum fluctuations, any of these could produce bursts that mimic artificial patterns through sheer cosmic coincidence. But that's the thrill of the mystery. Whether these signals are natural or not, they're forcing us to confront a humbling truth. The cosmos is stranger, more nuanced, and far more inventive than we've ever imagined. And until we know for sure, every prime-numbered pulse is a riddle waiting to be solved, one that might just rewrite our place in the universe. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, isn't your grandfather's telescope. Forget about domes and giant dishes. This revolutionary instrument looks more like a skate park half-pipe than a traditional observatory. Its 4 massive cylindrical reflectors, each as long as a football field, sit stationary in the Canadian wilderness, passively scanning the northern sky as Earth rotates beneath them. This unconventional design gives CHIME a superpower, the ability to monitor an area 200 times larger than the full moon continuously, relentlessly, without blinking. That's why it's become the ultimate fast radio burst hunter, catching signals that would slip through the fingers of conventional telescopes. What makes CHIME truly extraordinary isn't just its size, it's the brain behind the brawn. Every second, this telescope processes enough data to fill a laptop's hard drive, sifting through cosmic static for the telltale blips of FRBs. Its custom-built supercomputer analyzes radio waves across 1,000 frequencies simultaneously, running algorithms trained to spot bursts in real time. When CHIME detects something unusual like those 28 prime-numbered pulses, it instantly alerts observatories worldwide, turning Earth into one giant listening post. Without this rapid response network, those mysterious prime intervals might have been dismissed as glitches or interference. Instead, they're rewriting astronomy textbooks. The telescope's secret lies in its original purpose. CHIME was built to map hydrogen, the universe's most abundant element, across billions of light years. But its designers had the foresight to include a secondary system, a digital trap for transient signals. It's like building a security camera to watch your front porch. then discovering it also captures meteor showers. That adaptability proved crucial when FRBs started appearing. While other telescopes stare at tiny patches of sky for weeks, CHIME watches everywhere at once, making it perfect for catching these cosmic lightning strikes. Consider the challenge astronomers faced before CHIME. Fast radio bursts last milliseconds faster than the blink of an eye. Traditional telescopes might scan the right patch of sky once every few days, giving them lottery odds of catching a burst. Even if they got lucky, pinpointing the source was nearly impossible without multiple observations. CHIME changed the game. Its daily all-sky surveys mean it doesn't just stumble upon FRBs, it stalks them, building catalogs of repeating bursts that let scientists track their behavior over time. That's how those 28 prime-numbered intervals emerged from the noise, not as single curiosities, but as a pattern repeating across years of observations. Yet CHIME's greatest contribution might be what it reveals about our own limitations. Before this telescope, astronomers assumed FRBs were extraordinarily rare. Now we know they're happening constantly, thousands per day across the universe. The prime-numbered bursts are just the tip of the iceberg, hinting at phenomena we've barely begun to classify. With upgrades already underway, including sharper resolution and wider frequency coverage, CHIME promises to peel back even more layers of this cosmic onion. Every new detection raises fresh questions. Are there other numerical patterns hidden in the bursts? Do different types of sources produce distinct intervals? The answers could be streaming toward Earth right now, waiting for this unassuming array of metal pipes in the Canadian wilderness to catch them mid-flight. What's thrilling is how CHIME embodies the spirit of scientific discovery. Built for one purpose, it stumbled onto something far stranger, reminding us that the universe often speaks loudest when we're listening for whispers. As it continues its vigil, one thing's certain: the next big breakthrough in this cosmic whodunit might already be brewing in its data streams, a pulse, a pattern, perhaps even a message we've yet to decipher. Most fast radio bursts are cosmic one-hit wonders, flaring into existence with staggering energy, then vanishing forever into the dark. These one-off bursts outnumber their repeating cousins by hundreds to one, flashing just once across the sky like a match struck in a cavern. But that fleeting nature makes them maddeningly hard to study. Without a second act, astronomers are left scrambling to piece together clues from a single millisecond of data. It's like trying to reconstruct a symphony from a single note. That's why those 28 repeating bursts are so precious. Unlike their here today gone tomorrow counterparts, these cosmic repeaters keep coming back, offering scientists front-row seats to their encore performances. With each recurrence, researchers gather more fingerprints, subtle variations in brightness, polarization twists, shifts in frequency. These details paint a stark contrast between the two FRB families. One-off bursts often arrive with a telltale smear, their signals stretched thin after traversing vast intergalactic deserts. Repeaters, by comparison, tend to emerge from denser, more turbulent neighborhoods, places where magnetic fields twist space like taffy and charged particles whip through plasma at near light speeds. The environments alone hint at fundamentally different origins. Picture a lone wolf versus a pack. One-off bursts might be the death cries of catastrophic events, neutron stars collapsing into black holes, or asteroids vaporizing in the crushing grip of a magnetar's gravity. These are cosmic last stands, violent and final. Repeaters, on the other hand, seem to thrive in sustained chaos. Their sources persist, weathering conditions that would shred ordinary matter, somehow channeling energy into those eerily precise prime-numbered pulses. Then there's the energy puzzle. Single bursts often unleash more raw power in their brief existence than repeaters do across multiple eruptions. It's the difference between a grenade and a machine gun. One delivers overwhelming force in an instant, the other sustains controlled bursts over time. This split suggests different engines under the hood. If one-offs are cosmic explosions, repeaters might be more like cosmic dynamos, tapping into some renewable reservoir of energy we've yet to comprehend. But the most tantalizing difference lies in the patterns themselves. While one-off bursts arrive without warning, repeaters like these 28 adhere to mathematical rhythms that border on obsessive. Prime-numbered intervals don't emerge from random processes. They require either an astonishing natural coincidence or a mechanism that imposes order on chaos. That's what keeps astronomers up at night. Whether it's the resonant hum of a neutron star's crust or something far more speculative, these repeating bursts aren't just repeating. They're counting, and every time they pulse, they're daring us to crack their code. By studying both types side by side, scientists are assembling a cosmic Rosetta Stone, a way to translate the language of these enigmatic signals. Each new detection, whether a solo performer or a recurring act, adds another glyph to the lexicon, and slowly, painstakingly, we're learning to read the universe's most cryptic messages. One of the most compelling theories about these prime-numbered bursts imagines a cosmic lighthouse, a spinning neutron star or black hole whose beam sweeps past Earth at mathematically precise intervals. Picture a celestial beacon rotating just fast enough that its pulses arrive in counts of 2, 3, 5, 7. The physics here is delicate. For this to work, the object's spin would need to synchronize perfectly with its orbital motion, creating a resonant effect that filters out non-prime intervals. It's like a skipping stone across a pond. If the stone hits the water at just the right speed and angle, the splashes follow a rhythmic pattern. But in this case, the pond is space-time, and the stone is a stellar corpse spinning with eerie precision. Then there's the cipher theory, the idea that these bursts aren't just random emissions but a form of cosmic encryption. Some researchers propose that the source might be generating bursts through a process akin to a mathematical algorithm, perhaps even a natural computer of sorts. Imagine a neutron star's crust vibrating like a drumhead, with shock waves bouncing between magnetic field lines. Under specific conditions, these vibrations could amplify at prime-numbered harmonics, turning the entire star into a radio transmitter tuned to mathematical constants. It's a stretch, but so was quantum mechanics a century ago. What's fascinating is how these theories reflect a deeper truth. When nature throws us a curveball, science gets creative. Faced with a signal that defies conventional explanations, physicists have turned to abstract mathematics, extreme astrophysics, and even speculative models involving higher dimensions. Some have even revisited an old idea from the 1960s, that certain black holes might act as cosmic oscillators, ringing like bells at frequencies determined by their mass and spin. If those frequencies coincided with primes, the result could be bursts spaced like ticks on a universal clock. Yet for all their ingenuity, these theories share a common hurdle: the sheer improbability of multiple independent sources across the universe all converging on the same prime-numbered timing. It's one thing for a single exotic object to produce such a pattern by chance, but 28, that's like flipping a coin and getting heads 28 times in a row. The odds are so vanishingly small that it begs for a simpler explanation. Maybe there's a fundamental physical process we've overlooked, one that naturally favors primes in the same way crystals favor geometric shapes. The debate isn't just academic, it's a race against time. Every new burst detected could hold the key to cracking this cosmic code. Telescopes are now trained on these sources, watching for subtle variations that might reveal whether we're dealing with spinning stars, vibrating black holes, or something even more extraordinary. Until then, these prime-numbered pulses remain one of the universe's most tantalizing riddles. a reminder that the cosmos still has secrets we've only begun to glimpse. The moment astronomers detected those prime-numbered fast radio bursts, one name echoed through the scientific community like a ghost from the past: the WOW signal. Back in 1977, a radio telescope in Ohio picked up a 72-second burst so powerful, so unnervingly artificial seeming, that the astronomer who discovered it scribbled, "Wow," in red ink on the printout. For decades, that signal stood as the closest thing we had to potential proof of extraterrestrial intelligence until it vanished, never repeating, leaving behind only theories and tantalizing what-ifs. Now, with these repeating prime-numbered FRBs, we might be facing the WOW signal's sophisticated cousin, a pattern so precise it feels like a callback to humanity's own attempts at cosmic communication. What makes these bursts so provocative isn't just their timing, it's how neatly they align with the hallmarks of a technosignature, the telltale fingerprints of advanced technology. When scientists design experiments to search for alien civilizations, they prioritize signals that nature struggles to mimic: narrowband transmissions, repeating sequences, and yes, mathematical constants like prime numbers. These FRBs check multiple boxes. They're not just repeating, they're repeating with the numerical equivalent of a spotlight, flashing a sequence any technologically literate species would recognize as meaningful. It's as if the universe handed us a puzzle where the pieces fit a little too well. Organizations like the Breakthrough Listen Initiative aren't taking these coincidences lightly. Using some of Earth's most sensitive radio telescopes, they've trained their algorithms on these bursts, combing through the data for even subtler patterns, hidden harmonics, encoded pulses, anything that might whisper artificial. So far, the bursts have resisted decoding. No prime counting sequences spell out the digits of pi, no intervals map to atomic elements, but absence of evidence isn't evidence of absence. Consider how humanity's own interstellar messages, like the Arecibo transmission, were designed: simple, universal, and deliberately distinct from natural noise. If an alien civilization sent a beacon, they'd likely prioritize detectability over complexity, knowing the signal might degrade across billions of light years. The scientific community remains cautiously divided. Skeptics point to the universe's knack for producing phenomena we once thought impossible: pulsars, quasars, gamma-ray bursts, all initially mistaken for potential alien signals until natural explanations emerged. Optimists counter that dismissing these FRBs outright risks the very bias that has historically stifled scientific progress. After all, the line between natural and artificial blurs when confronting civilizations potentially millions of years more advanced than ours. Their technology might harness physics we haven't discovered yet, rendering their signatures indistinguishable from what we'd call natural phenomena. Here's the paradox at the heart of the search. The more extraordinary a signal seems, the more rigorously science must vet it. Yet the very act of demanding incontrovertible proof might mean waiting forever. These prime-numbered bursts exist in the tantalizing middle ground, too strange to ignore, too ambiguous to confirm. Whether they're the product of magnetars vibrating like cosmic tuning forks or something far more profound, one thing is certain: they've reignited humanity's oldest question with fresh urgency. Every time another prime-counted pulse streaks across the cosmos, it's not just a mystery to solve, it's a mirror held up to our own longing to connect with whatever or whoever else might be out there. Studying fast radio bursts is like trying to photograph lightning with a disposable camera. By the time you press the button, the moment's already gone. These cosmic flashes vanish in milliseconds, leaving astronomers scrambling to piece together clues from the faintest of echoes. But the challenges don't stop there. Interstellar gas clouds stretch and smear the signals as they travel billions of light years, like a message written on rubber bands and pulled taut. For ordinary bursts, that's problematic enough, but for those 28 repeating bursts with their prime-numbered precision, the margin for error is razor-thin. A single millisecond of distortion could turn a sequence of 7, 11, 13 into cosmic static, erasing the pattern that makes these signals so extraordinary. Detecting these bursts requires telescopes with reflexes faster than a hummingbird's wings. Traditional observatories designed to study slow, steady objects like galaxies or nebulas often miss FRBs entirely. Their instruments simply aren't built to capture millisecond flashes. That's why next-generation arrays like CHIME and the Deep Synoptic Array are revolutionizing the hunt. These telescopes don't just look at the sky, they listen to it, processing petabytes of radio waves in real time with algorithms trained to spot the digital equivalent of a needle in a haystack. Even then, catching a burst is only half the battle. Pinpointing its origin demands a global network of telescopes working in unison, triangulating the signal across continents as if the Earth itself were one giant antenna. Then there's the noise problem. Our own planet is a cacophony of radio interference. Cell phones, satellites, even microwaves leaking radiation can masquerade as cosmic signals. Distinguishing a genuine FRB from terrestrial static is like trying to hear a whisper in a hurricane. For the prime-numbered bursts, the stakes are even higher. Their patterns are so precise that a single misidentified pulse could derail years of research. That's why observatories now employ artificial intelligence to filter out false positives, teaching machines to recognize the unique fingerprint of an FRB amidst humanity's radio chaos. But perhaps the greatest challenge lies in the bursts themselves. Unlike pulsars or quasars, which follow predictable rhythms, FRBs refuse to play by rules we understand. The prime-numbered intervals defy conventional astrophysics, leaving researchers to wonder, are we dealing with a new class of celestial object or a flaw in our own assumptions? Every theory from magnetar flares to alien beacons runs headlong into the same wall of cosmic ambiguity. The universe, it seems, enjoys keeping its mysteries just out of reach. Yet for all the obstacles, the hunt continues. Each new detection, each flicker of data, brings us closer to unraveling the enigma. Telescopes grow more sensitive, algorithms sharper, collaborations more seamless. And somewhere in the void, those 28 bursts keep counting primes, as if waiting for us to finally catch up. The challenges may be immense, but so is the reward. A glimpse into the universe's best-kept secrets, 1 millisecond at a time. History has a funny way of humbling our cosmic ambitions. Just ask the astronomers who first detected pulsars in 1967. When Jocelyn Bell Burnell and her colleagues picked up those eerily regular radio pulses from deep space, their initial reaction wasn't awe, it was bewilderment. The signals arrived with such clockwork precision that they jokingly labeled them LGM1, short for Little Green Men. For a brief, electrifying moment, the world held its breath, wondering if we'd finally intercepted a message from another civilization. But the truth, as it often is in science, was both more mundane and more extraordinary. These weren't alien broadcasts, they were the death throes of spinning neutron stars, cosmic lighthouses beaming radiation across the galaxy. The lesson: the universe has a knack for conjuring phenomena so precise, so seemingly deliberate, that they blur the line between nature and intelligence. Fast forward to 1977, and history nearly repeated itself with the WOW signal, a 72-second burst of radio waves so intense, so unnervingly artificial, that the astronomer who spotted it scrawled, "Wow." In the margin of the printout, Like the pulsars before it, this signal seemed too perfect to be random noise. Yet despite decades of searching, it never repeated, fading into legend as either a fluke of nature or a missed connection with something beyond our understanding. These episodes aren't just footnotes in astronomy textbooks, they're cautionary tales. Time and again, we've projected our hopes onto the cosmos, only to find that reality is stranger than we imagined. Now enter these 28 prime-numbered fast radio bursts. They're the latest chapter in a long tradition of cosmic false alarms, or perhaps this time something more. Like pulsars and the wow signal before them, they defy easy explanation, straddling that tantalizing edge between natural wonder and engineered artifact. But here's what's different. While past mysteries were eventually resolved, these bursts stubbornly resist classification. Pulsars had a clear mechanism, spinning neutron stars. The wow signal, for all its intrigue, was a one-off. These FRBs, they're neither. They repeat, but not randomly. They pulse, but with mathematical elegance that feels almost contrived. It's as if the universe is testing us, asking how much ambiguity we can tolerate before jumping to conclusions. What's fascinating is how each of these episodes, from LGM-1 to the wow signal to today's prime counting bursts, has expanded our cosmic vocabulary. Before pulsars, no one imagined neutron stars could spin hundreds of times per second. Before FRBs, we didn't know the universe could produce millisecond flashes brighter than galaxies. Every false alarm has, paradoxically, led to real discovery, pushing science to invent new categories, new physics, even new ways of listening to the stars. So where does that leave us with these 28 bursts? However this mystery unfolds, whether it's magnetars performing feats we can't yet explain or something far more speculative, one thing's certain: they're already doing what cosmic anomalies do best. They're stretching our definitions, challenging our assumptions, and reminding us that the universe has a sense of humor. After all, what could be more poetic than nature trolling us with the very patterns we'd used to signal our own existence? The irony isn't lost on scientists. As we scan the skies for signs of others, we might just be decoding the universe's way of saying, "You're not as clever as you think." And that, in itself, is a discovery worth making. Prime numbers are the universe's hidden architects, silent, indivisible, and lurking beneath the surface of everything from butterfly wing patterns to the spirals of galaxies. Unlike ordinary numbers that can be broken down into smaller factors, primes stand alone, stubbornly resisting division. That's what makes their appearance in fast radio bursts so mind-bending. These aren't just random digits, they're the foundational language of mathematics itself, appearing where we least expect them, in the chaotic depths of space. Take encryption, for example. Every time you send a secure message online, primes are working behind the scenes. Modern cryptography relies on multiplying two massive prime numbers, a calculation easy to perform but nearly impossible to reverse without the key. It's a lock only mathematics can pick. Now imagine that same principle scaled up to cosmic proportions. If nature, or something else, is using primes to structure these bursts, it's employing a universal cipher, one that any intelligent civilization would recognize. That's the tantalizing parallel here. Primes aren't just numbers, they're a cross-cultural handshake, a way to shout across the void and say, "This is no accident." But could natural processes really produce such pristine patterns? Physicists have spent years modeling scenarios, from neutron star quakes to black hole echoes, searching for a mechanism that might spit out primes. One intriguing idea involves resonance, the same phenomenon that makes a wine glass shatter at the right pitch. If a dense stellar object vibrates at specific frequencies, its pulses could amplify at prime intervals, like harmonics on a cosmic guitar string. Another theory borrows from chaos theory, suggesting turbulent plasma around magnetars might collapse into ordered bursts under extreme magnetic stress. Yet none of these models fully explain the precision of those 28 bursts. They're too clean, too exact, as if the universe is showing off a trick we haven't learned yet. The collaboration between mathematicians and astronomers has sparked something revolutionary. Number theorists, who usually dwell in abstract realms, are now poring over astrophysical data, while astronomers are delving into modular forms and prime gaps. It's a meeting of disciplines that rarely overlap, and the questions they're asking are rewriting textbooks. Could prime-numbered bursts reveal new states of matter? Might they hint at physics beyond the standard model, like quantum gravity effects near black holes? Every hypothesis pushes the boundaries of both fields, proving that the cosmos still holds puzzles not even our sharpest minds have dreamed up. What's striking is how primes bridge the abstract and the tangible. They appear in cicada life cycles. Some species emerge only every 13 or 17 years, primes that minimize overlap with predators. Crystals grow along prime-numbered symmetries, and even the distribution of galaxies clusters around these numbers. Now, with fast radio bursts echoing that same order, we're forced to confront a haunting possibility. Primes might be more than a quirk of math. They could be woven into the fabric of reality itself, a hidden rhythm the universe falls back on when it wants to be heard. Whether these bursts are nature's symphony or something more, one thing's clear: the cosmos is counting, and we're only just beginning to understand the language. The hunt for fast radio bursts has become astronomy's version of a high-stakes treasure hunt, with telescopes across the globe acting as synchronized nets cast into the cosmic ocean. In the remote hills of British Columbia, Canada's CHIME telescope scans the sky like a relentless sentinel, its massive cylindrical arrays capturing radio whispers from the edge of the universe. Halfway around the world, Australia's Parkes Observatory, nicknamed the Dish, listens with equal intensity, its 64-meter parabolic antenna tuned to catch the faintest blips from the southern skies. These instruments, separated by oceans and continents, now share data in real time, their observations stitched together into a seamless tapestry of discovery. It's a testament to how modern science operates. No single telescope, no solitary genius can unravel mysteries this profound. What's driving this unprecedented collaboration? Those 28 prime-numbered bursts rewrote the playbook. Before their discovery, FRB research was fragmented, isolated teams working in silos, often duplicating efforts or missing crucial patterns in the noise. But the moment those repeating primes emerged, everything changed. Suddenly, the race wasn't just about detecting bursts, it was about decoding a cosmic cipher that demanded global attention. Telescopes from China's 500-meter aperture spherical radio telescope, or FAST, to Europe's low-frequency array began coordinating observations, their combined power creating a virtual super telescope spanning the planet. When one instrument catches a burst, alerts flash across research networks within seconds, directing other observatories to train their dishes on the same patch of sky. This isn't just scientific cooperation, it's a paradigm shift. Historically, astronomical discoveries were guarded like state secrets, with teams hoarding data for competitive advantage. But FRB, especially these mathematically charged ones, have shattered that model. Projects like the Deep Synoptic Array in California and South Africa's SETI openly share terabytes of raw data, inviting physicists, mathematicians, and even amateur astronomers to scour the numbers for clues. Online platforms now host crowdsourced analyses where machine learning algorithms sift through noise alongside human intuition. The result, a democratization of discovery, where breakthroughs can come from anywhere: a university lab, a high school classroom, or a programmer's basement halfway across the world. The urgency is palpable. Every new prime-numbered burst captured adds another data point to the puzzle. Teams in Australia might pinpoint a burst's origin galaxy, while Canadian researchers analyze its polarization and European scientists model its dispersion. Like detectives piecing together a suspect's movements, each observation narrows the possibilities. Is the source orbiting another star, its pulses varying as it moves? Does the signal's twist reveal the strength of intergalactic magnetic fields it traversed? The questions multiply faster than answers, but the collaborative engine driving this search never slows. What's remarkable is how these efforts mirror the very signals they're chasing. Just as the prime-numbered bursts repeat with precision, so too does this global network pulse with activity, methodical, synchronized, relentless. It's a reminder that humanity's greatest discoveries rarely come from lone flashes of brilliance, but from countless minds working in concert, each adding a stroke to the larger picture. And somewhere out there, amidst the static and the stars, those 28 bursts keep counting primes, as if waiting for the moment our collective effort finally cracks their code. What if fast radio bursts aren't just cosmic anomalies, but cracks in the fabric of reality itself? It's a theory that sounds ripped from science fiction, yet some physicists are seriously considering whether these enigmatic signals could be echoes from other dimensions or even parallel universes. At the heart of this audacious idea lies a simple truth. FRBs defy conventional astrophysics so thoroughly that they've become a blank canvas for humanity's boldest cosmological conjectures. Picture our universe as a sheet of paper. Most cosmic events, supernova, black hole collisions, happen within that flat plane. But what if FRBs are like creases in the paper, points where something from outside presses in, releasing bursts of energy as realities brush against one another? The math behind this is mind-bending but not implausible. String theory, for instance, suggests our universe might float in a higher dimensional bulk, with other universes just millimeters away in dimensions we can't perceive. Under extreme conditions like near a black hole's singularity, these dimensions could briefly interact, producing energy discharges that manifest as FRBs. It's akin to two soap bubbles touching. The moment of contact releases energy, then they separate, leaving no trace. If FRBs are these fleeting touches, their prime-numbered intervals might reflect some deeper dimensional harmony, like cosmic harmonics vibrating across membranes of reality. Even skeptics admit the theory has intriguing hooks. FRBs emit energy in ways that mirror predicted signatures of higher dimensional events, like their bizarre polarization patterns, which some models suggest could stem from space-time itself twisting in ways our physics can't yet describe. Then there's their distribution. Unlike most cosmic phenomena tied to galaxies, FRBs appear evenly scattered across the sky, as if they're not bound to any single location in our three-dimensional space. Could that uniformity hint at something outside the framework we know? Of course, the multiverse angle remains fringe science, brilliant speculation rather than settled fact. Critics argue it's the modern equivalent of attributing thunderstorms to Zeus, a placeholder explanation for phenomena we don't yet understand. But here's what's undeniable. FRBs have become a catalyst for reimagining reality's boundaries. Whether they're proof of parallel universes or not, their very existence is stretching cosmology in thrilling new directions. Every prime-numbered pulse invites us to wonder, are we hearing the universe's heartbeat, or the whisper of something far stranger just beyond the veil? The Fermi paradox has haunted astronomers for decades, a simple question with no easy answer. If the universe is teeming with life, why does it feel so silent? Where are the interstellar cities, the cosmic beacons, the unmistakable signs of civilizations beyond our own? The prime-numbered fast radio bursts might not solve the paradox, but they've thrown gasoline on the debate. Imagine a galaxy where advanced beings don't build megastructures or send probes. Instead, they broadcast in the oldest, most universal language, mathematics. Primes are the perfect calling card, indivisible, unmistakable, impossible to fake. If you wanted to announce your presence to the cosmos without revealing your location, this might be how you'd do it. But here's the twist. The Fermi paradox assumes that advanced civilizations would be loud, flooding the galaxy with signals or artifacts. These bursts suggest another possibility. Maybe they're not silent, just subtle. Their messages could be drifting past us all the time, hidden in plain sight, disguised as cosmic static. We've spent decades listening for deliberate, complex transmissions. What if we've been overlooking the equivalent of a cosmic handshake? The prime-numbered intervals could be the universe's way of whispering, "We're here, but you'll have to pay attention." Critics argue this is wishful thinking, that nature is perfectly capable of producing strange patterns without intelligence behind them. After all, pulsars were once mistaken for alien signals until science caught up. But supporters counter that dismissing the idea outright risks repeating history's mistakes. When Galileo pointed his telescope at Jupiter's moons, the establishment refused to look, convinced the heavens were unchanging. Today, we face a similar crossroads. Are these bursts just another cosmic quirk, or could they be the first faint hints of a galactic conversation we're only beginning to decode? The paradox grows richer with every new detection. If civilizations are out there, why haven't they colonized the galaxy? Maybe they have, but not in ways we recognize. Advanced beings might transcend physical expansion, opting instead to embed their presence in the fabric of physics itself. These bursts could be their legacy, a way to say we existed long after their stars have burned out. Or perhaps their probes, autonomous beacons drifting through the void, programmed to signal in primes until someone answers. Whatever the truth, these bursts have done something remarkable. They've turned the Fermi paradox inside out. Instead of asking why we haven't found aliens, we're now asking whether we've been looking for the wrong things all along. The cosmos might not be empty, just stranger than we imagined. And as we stand on the edge of this revelation, one thing is certain. The universe has a way of humbling our assumptions, reminding us that the search for meaning is never as simple as it seems. The pursuit of fast radio bursts isn't just expanding our cosmic horizons, it's reshaping the very tools we use to explore them. To catch these fleeting signals, scientists have pushed telescope technology beyond its limits, designing arrays like CHIME that process data at speeds once thought impossible. These innovations aren't confined to astronomy. The same ultra-sensitive radio receivers developed to pick up FRBs from billions of light years away are now being adapted to improve satellite communications, reducing interference and boosting signal clarity across global networks. Imagine streaming high-definition video from a remote village or a ship in the middle of the ocean with near-instantaneous clarity. That's the real-world potential bubbling up from this cosmic detective work. Then there's the AI revolution. Sifting through the avalanche of data from radio telescopes requires algorithms so advanced they can spot a millisecond burst buried in years of cosmic static. Machine learning models trained on FRB hunts are now finding applications everywhere, from medical imaging to fraud detection. Their pattern recognition skills honed by the ultimate challenge, finding order in the universe's chaos. One team repurposed an FRB detection algorithm to monitor earthquakes, where it identified subtle tremors traditional systems had missed. It's as if the cosmos handed us a masterclass in problem solving, teaching our machines to see what human eyes alone cannot. But perhaps the most unexpected spin-off lies in navigation. Deep space missions currently rely on Earth-based radio signals, which grow weaker over interstellar distances. FRB research has inspired a radical alternative, using the bursts themselves as cosmic lighthouses. By timing their arrivals across multiple spacecraft, future probes could triangulate their positions with unprecedented accuracy, even far beyond the solar system. It's like swapping a compass for a constellation of pulsars, a natural GPS written into the fabric of the universe. Quantum computing, too, is feeling the ripple effects. Decoding the complex polarization patterns of FRBs has led to breakthroughs in error correction codes, the very same technology needed to stabilize fragile quantum bits. Some labs are already testing these codes in prototype quantum processors, where they're proving remarkably effective at filtering out noise. What began as an attempt to understand mysterious space signals might just unlock the next leap in computing power. The beauty of this technological feedback loop is its unpredictability. No one building CHIME receivers imagined they'd one day help beam the internet to underserved regions. Programmers training AI to hunt FRBs didn't set out to revolutionize medical diagnostics. Yet here we are, witnessing how curiosity-driven science, the simple act of staring at the sky and asking, "What's that?" can cascade into innovations that touch every corner of human life. The universe, it seems, rewards those who listen closely, not just with answers, but with tools we didn't know we needed. And as telescopes grow sharper and algorithms smarter, one thing's certain: the next burst could spark a breakthrough we can't even imagine yet. Humanity has always been drawn to cosmic mysteries like moths to a flame, and fast radio bursts, especially those ticking away in prime numbers, have ignited imaginations like few discoveries before them. Within hours of the first prime-numbered burst announcement, social media exploded with theories ranging from alien Morse code to interdimensional doorbells. Science journalists scrambled to explain the phenomenon, while late-night talk show hosts cracked jokes about extraterrestrial mathematicians. The very idea that the universe might be counting primes feels ripped from a sci-fi novel, which is precisely why these bursts have become cultural lightning rods. They tap into our deepest hopes and fears about what, or who might be out there in the dark. Documentary filmmakers have seized on the drama, framing FRB hunters as modern-day Indiana Joneses chasing spectral treasures. Streaming platforms now feature glossy specials where astronomers huddle over monitors, their faces lit by the glow of mysterious radio waves, while dramatic narration asks, "Is this the message we've been waiting for?" Even Hollywood took notice. Recent blockbusters have woven FRB-like signals into their plots, imagining them as everything from alien distress calls to cosmic breadcrumbs leading to ancient artifacts. The line between fact and fiction blurs effortlessly when reality serves up something this inexplicable. Online forums buzz with grassroots analysis, where amateur astronomers and math enthusiasts dissect every new burst like detectives at a crime scene. Reddit threads overflow with annotated signal graphs, while YouTube explainers rack up millions of views from audiences hungry for both science and speculation. Some see divine patterns in the primes, while others meticulously debunk extraterrestrial theories with astrophysical equations. The beauty of this public dialogue lies in its democratization. You no longer need a PhD to participate in one of astronomy's greatest ongoing mysteries. What's fascinating is how these bursts mirror historical moments when science collided with public wonder. The discovery of pulsars in the 1960s sparked similar fervor, as did the WOW signal decades later. But prime-numbered FRBs have added a new twist. They're not just anomalies, they're elegant anomalies. There's an artistry to their timing that feels almost theatrical, as if the cosmos is staging a grand performance. Museums have even incorporated them into exhibits where visitors can hear the bursts converted into musical notes, haunting staccato rhythms that make abstract math suddenly visceral. This collective fascination reveals something profound about our species. We're pattern-seeking creatures, hardwired to find meaning in randomness. When the universe serves up a sequence as pristine as 2, 3, 5, 7, it's irresistible not to wonder, is this noise or a signal? Science demands patience and proof, but the public's embrace of these bursts celebrates something equally vital: the joy of not knowing. Every prime-numbered pulse is a reminder that the cosmos still holds wonders beyond our comprehension, and that alone is worth celebrating. Whether they're natural or not, these bursts have already achieved something remarkable. They've made millions look up from their screens and ponder the infinite, if only for a moment. Fast radio bursts have inspired everything from groundbreaking science to wild conspiracy theories, but separating fact from fiction is trickier than it seems. Take the most persistent myth that these bursts are definitive proof of extraterrestrial intelligence. While the prime-numbered intervals make for an irresistible story, science demands more than intriguing patterns. Extraordinary claims require extraordinary evidence, and so far, no burst has carried encoded information, modulated signals, or any other hallmark of deliberate communication. That doesn't mean the possibility should be dismissed outright, but it does mean we're far from shouting "Eureka!" Yet this nuance often gets lost in sensational headlines, leaving the public with whiplash between aliens confirmed and just space noise. On the flip side, some skeptics go too far in the opposite direction, dismissing FRBs as meaningless cosmic static. This overlooks the meticulous research confirming their extragalactic origins. These aren't random blips from malfunctioning satellites or atmospheric interference. They're violent, high-energy events stamped with the fingerprints of distant galaxies. The prime-numbered repeats, in particular, defy simplistic explanations. Calling them noise is like dismissing a symphony as random violin screeches because you haven't learned to read sheet music yet. The truth lies somewhere in the middle. FRBs are neither deliberate alien messages nor meaningless glitches, but natural phenomena pushing the boundaries of what we thought possible. Another common misconception is that all fast radio bursts are created equal. In reality, the one-off bursts and the repeating prime-numbered ones might as well be different species. Single bursts often originate in environments suggesting catastrophic, one-time events like neutron stars collapsing into black holes. Repeaters, by contrast, seem tied to persistent sources, possibly orbiting objects or magnetars with unstable magnetic fields. Conflating the two obscures the diversity of these cosmic phenomena, like assuming all bright lights in the sky must be airplanes when some are meteors, planets, or distant supernova. Then there's the myth of immediacy, the idea that solving the FRB puzzle is just one aha moment away. In reality, science rarely works in dramatic breakthroughs. Pinpointing the first repeating FRB took years of patient observation, and deciphering the prime-numbered intervals will likely take even longer. Each new detection adds complexity. Some bursts drift in frequency, others show substructure, and a few even exhibit echoes hinting at turbulent surroundings. These nuances don't fit neatly into viral sound bites, but they're the breadcrumbs leading us toward real understanding. Perhaps the most damaging myth is that curiosity about extraterrestrial origins undermines scientific rigor. Wonder and skepticism aren't opposites, they're two sides of the same coin. The scientists hunting FRBs balance open-mindedness with analytical precision, weighing every hypothesis against the evidence. When they entertain the idea of artificial origins, it's not because they've abandoned reason, but because excluding possibilities prematurely is just as unscientific as accepting them uncritically. The history of astronomy is littered with discoveries initially mistaken for something else, pulsars dubbed LGM signals, quasars misclassified as nearby stars. Progress happens when we ask what if, while keeping our feet firmly planted in the what is. Debunking these myths isn't about stifling imagination, it's about channeling it productively. The reality of FRBs is thrilling enough without embellishment. Cosmic events so powerful they outshine galaxies, repeating with mathematical precision we can't yet explain. Whether their source turns out to be exotic physics or something even more extraordinary, the journey to unraveling them is a testament to science at its best, patient, collaborative, and endlessly curious. And in a world hungry for easy answers, that's a story worth telling straight. The Square Kilometer Array isn't just another telescope, it's a revolution waiting to happen. Spread across 2 continents with thousands of radio dishes in South Africa and Australia, this colossal observatory will scan the sky with 50 times the sensitivity and 10,000 times the speed of current instruments. When it comes online in the late 2020s, the SKA could detect dozens of fast radio bursts every single day, transforming what's now a trickle of data into a fire hose. Imagine going from studying a handful of exotic fish to diving into an entire ocean teeming with life. That's the leap astronomers are about to make, and buried in that flood of detections might be the key to unlocking the prime-numbered burst's deepest secrets. What makes the SKA so groundbreaking isn't just its scale, it's the precision. Current telescopes like CHIME excel at catching bursts but struggle to pinpoint their exact origins. The SKA's unprecedented resolution will act like cosmic GPS, tracing FRBs back to their home galaxies with pinpoint accuracy. For those enigmatic prime-numbered sequences, this could be the breakthrough moment. If they're tied to neutron stars, for instance, the SKA might catch their host galaxies mid-flare, revealing companion stars or debris disks that trigger the bursts. If they're artificial, the array's fine-tuned receivers could uncover subtle modulations, tiny frequency drifts, or polarization twists that natural processes can't easily explain. But the SKA isn't working alone. A new generation of space-based observatories, like the European Space Agency's Advanced Telescope for High-Energy Astrophysics, will complement its efforts by scanning for X-ray and gamma-ray counterparts to FRBs. It's the difference between hearing a knock on the door and peering through the peephole to see who's there. Together, these instruments might catch a prime-numbered burst erupting alongside gravitational waves or a neutrino shower, a smoking gun linking them to cataclysmic events like magnetar eruptions or black hole mergers. The real game-changer, though, could be artificial intelligence. With the SKA generating petabytes of data daily, machine learning algorithms will sift through the noise for patterns no human could spot. Already, neural networks trained on existing FRBs have uncovered subtle sub-burst structures and hidden periodicities. Applied to prime-numbered sequences, these tools might detect nested rhythms, primes within primes, or geometric progressions that hint at underlying mechanisms. Some astronomers even speculate that AI could recognize linguistic or mathematical signatures if the bursts carry encoded information, though that remains firmly in the realm of speculation. Yet for all its potential, the SKA's greatest gift might be humility. Every major leap in observational power, from Galileo's telescope to Hubble, has revealed how much we didn't know. As we finally capture FRBs in bulk, we'll likely encounter behaviors that defy current theories. Perhaps prime-numbered bursts will prove to be just one flavor in a vast cosmic menagerie, their patterns overshadowed by even stranger phenomena. Or perhaps they'll resolve into something startlingly simple, a natural process so elegant we'll wonder how we ever missed it. One thing's certain, solving this puzzle will redefine astronomy. Cracking the prime-numbered FRB code could rank alongside discovering dark energy or gravitational waves, a paradigm shift revealing entirely new physics, or just maybe, our first glimpse of intelligence beyond Earth. The SKA won't just listen to the cosmos, it might finally let us hear its language. And when that moment comes, the universe won't just feel bigger, it'll feel infinitely more mysterious and more wondrous than we ever dared dream. If fast radio bursts were confirmed as artificial signals, humanity would face dilemmas with no precedent in our history. The moment we recognize an intentional message from beyond Earth, every assumption about our place in the cosmos shatters, and with it comes a tidal wave of ethical questions. Should we respond immediately, broadcasting our presence to a civilization that might be millions of years more advanced? Or would that recklessly expose humanity to risks we can't possibly calculate? These aren't hypotheticals anymore. With prime-numbered bursts ticking away like a cosmic countdown, the debate has shifted from academic speculation to urgent necessity. The scientific community isn't flying blind. Protocols like the 1989 Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence provide a framework, albeit an untested one. Drafted by the International Academy of Astronautics, these guidelines emphasize verification, transparency, and international consultation before any response. But here's the catch: they're voluntary. No global governing body enforces them, and in an era where private companies operate radio telescopes capable of interstellar communication, a single billionaire could theoretically bypass consensus. The stakes are staggering. A poorly crafted reply might inadvertently broadcast sensitive biological or geopolitical information, or worse, trigger hostility from a civilization whose motives we can't fathom. Then there's the question of who speaks for Earth. Unlike fictional first contact scenarios with unified planetary governments, humanity remains fractured by borders, ideologies, and competing interests. Would a response require unanimous UN approval, or would scientific bodies like the International Astronomical Union take the lead? Historically, attempts to send messages like the Arecibo transmission in 1974 or the Pioneer plaques were unilateral decisions by small groups. Today, with social media amplifying every dissent, achieving global consensus seems impossible. Yet the prime-numbered bursts demand exactly that, a collective voice representing all 8 billion of us, not just the technologically empowered few. Security experts warn of more terrestrial dangers. Confirmation of an extraterrestrial signal could destabilize economies, ignite religious movements, or spark panic. During the 1938 War of the Worlds, radio broadcast a fictional account of Martian invasion. Mass hysteria erupted despite clear disclaimers. In our hyper-connected era, misinformation could spread faster than facts. Governments might hoard data, fearing leaks could cause unrest. And what if the signal's content is unsettling? A repeating prime sequence might be benign, but what if future bursts contain instructions for building advanced technology or warnings of existential threats? The very act of deciphering could become a geopolitical flashpoint, with nations racing to exploit or suppress knowledge. Ethicists raise quieter but equally profound concerns. Responding to an extraterrestrial signal assumes the sender operates on timescales compatible with human lifespans. Given the vast distances between stars, a dialogue could span centuries. Are we ethically obligated to continue a conversation our great-grandchildren might inherit? Conversely, is silence a form of cosmic rudeness or self-preservation? The prime-numbered bursts add a chilling twist. Their mathematical purity suggests patience and longevity. Whatever's sending them might expect reciprocity in kind, playing a game with rules we don't yet grasp. Perhaps the most humbling realization is how unprepared we are, not just logistically, but psychologically. For millennia, humans have gazed at the stars and wondered if we're alone. Now, standing at the threshold of an answer, we confront the weight of that curiosity. The prime-numbered bursts don't just challenge our science, they hold up a mirror to our fractured world, demanding we grow up as a species before reaching into the cosmic dark. Whether they're natural or not, they've already given us a gift, the chance to imagine for the first time in history what it truly means to not be alone in the universe, and what we owe to whatever or whoever might be listening back. The precision of these prime-numbered bursts doesn't just defy expectations, it warps our fundamental understanding of time. Imagine a cosmic metronome ticking not in seconds or minutes, but in primes, its rhythm unshaken across billions of light years. This isn't just about counting, it's about the very fabric of reality. Time, as we know it, is supposed to be fluid, relative, shaped by gravity and motion. Yet here are signals arriving with intervals so exact, they hint at a universal clockwork deeper than Einstein's spacetime. Could these bursts be tapping into something beyond our current physics, a layer of reality where time isn't continuous but quantized, ticking in discrete, prime-numbered steps? Some theorists are chasing a radical idea that fast radio bursts might be natural synchronizers, cosmic phenomena that lock to universal rhythms we can't yet perceive. Picture the universe as a vast orchestra with FRBs as the conductor's baton, coordinating events across unimaginable distances. In quantum gravity models, space-time itself might have a granular structure at microscopic scales, like pixels on a screen. If these bursts originate near extreme objects like black holes, where quantum gravity effects dominate, their prime-numbered intervals could reflect this underlying granularity. It's as if we're glimpsing the universe's refresh rate, the hidden cadence at which reality updates. Then there's the eerie possibility of temporal entanglement, the notion that these bursts aren't just marking time, but actively weaving it. In quantum mechanics, particles can become entangled, their states linked instantaneously across space. Could FRBs be macroscopic versions of this phenomenon, their pulses entangled across cosmic distances, creating a web of synchronized events? It sounds like science fiction, but consider this. If two bursts separated by billions of light years share the same prime interval, is that coincidence or evidence of a deeper connection? The implications would rewrite physics, suggesting that time itself might be a collective phenomenon, not just a backdrop to the universe, but an active participant. Of course, skepticism is healthy. Mainstream physics still lacks a unified theory of quantum gravity, and attributing FRBs to exotic spacetime effects remains speculative. Yet history shows that breakthroughs often emerge from the fringe. Pulsars, once mistaken for alien signals, revealed neutron stars, objects so dense they bend the rules of matter. Could these bursts be the next chapter in that story, pointing toward physics we've yet to dream up? The answer might lie in the data itself. Future telescopes could detect subtle anomalies in burst timing, tiny deviations that betray the influence of quantum spacetime foam or extra dimensions. Until then, these prime-numbered pulses stand as both challenge and invitation, daring us to rethink not just what we know about the cosmos, but how we measure its very heartbeat. What's undeniable is how these bursts stretch our imagination. They force us to confront the possibility that time isn't what we thought, that beneath the smooth flow of seconds and centuries, the universe might be counting in primes, its rhythm echoing through the dark. Whether that's poetry or physics remains to be seen, But one thing's certain, the deeper we listen, the stranger reality becomes. History has a peculiar way of turning celestial discoveries into cultural earthquakes. When Galileo first pointed his telescope at Jupiter's moons in 1610, he didn't just spot celestial bodies, he shattered an entire worldview. Overnight, the Earth was no longer the center of the universe, and the shockwaves rippled far beyond astronomy, upending philosophy, religion, and art. Centuries later, Hubble's deep field images did something equally profound. They transformed distant pinpricks of light into a cosmic tapestry of galaxies, making the universe feel both vast and intimate. Now, as we stand on the brink of deciphering prime-numbered fast radio bursts, we might be witnessing the birth of another paradigm shift, one where mathematics and cosmic mystery collide to redefine how we see our place in the cosmos. Artists have already begun weaving these enigmatic signals into their work. Contemporary composers are translating FRB sequences into musical scores, their prime-numbered intervals lending an otherworldly rhythm to symphonies. Visual artists, inspired by the burst's fleeting brilliance, are crafting installations that pulse with light at prime intervals, creating immersive experiences that blur the line between science and wonder. Even fashion designers have embraced the aesthetic, embedding Fibonacci spirals and prime sequences into textiles, as if wearing the universe's hidden code. This isn't just creativity, it's a cultural conversation, a way to grapple with the awe these bursts inspire. In classrooms, FRBs are becoming a gateway to STEM. Teachers report that students who once yawned at algebra light up when primes are framed as cosmic clues. A high school in Norway recently used the bursts to design a cross-disciplinary project. Math students calculated prime intervals, physics classes modeled radio wave dispersion, and literature students wrote speculative fiction about the signal's origins. It's a testament to how mysteries like these can dissolve the artificial walls between subjects, revealing knowledge as a unified pursuit. Philosophers, too, are leaning into the fray. The prime-numbered bursts have reignited debates about the nature of intelligence itself. If mathematics is truly universal, a language any civilization might share, does that mean logic and reason are inevitable outcomes of cosmic evolution? Or are we projecting human biases onto the void? These questions echo through academic journals and coffeehouse discussions alike, proving that some discoveries don't just add to our knowledge, they rearrange how we think. Perhaps the most profound impact lies in how these bursts are democratizing wonder. Unlike elite telescopes of the past, modern FRB data is often public, inviting amateur astronomers and citizen scientists to join the hunt. Online forums buzz with analyses from retirees, teenagers, and taxi drivers, all united by the thrill of the unknown. In an era of division, the bursts have become rare common ground, a reminder that the universe speaks a language everyone can yearn to understand. The true legacy of these prime-numbered signals may not be the answers they provide, but the questions they force us to ask. Like Galileo's moons or Hubble's galaxies, they're nudging humanity toward humility and curiosity. Whether they're natural or not, they've already done something extraordinary. They've made the cosmos feel alive with possibility, a place where numbers dance and the stars might just be counting along. The prime-numbered fast radio bursts aren't just an astronomy problem, they're a cosmic crossword puzzle, demanding expertise from fields that rarely intersect. Picture a team of mathematicians hunched over signal data, tracing prime sequences like detectives following a trail of breadcrumbs, while astrophysicists map the bursts to violent stellar phenomena light years away. Meanwhile, computer scientists train neural networks to spot subtle patterns invisible to the human eye, and linguists analyze the burst structure for hallmarks of symbolic communication. This isn't just collaboration, it's a full-scale intellectual renaissance where the boundaries between disciplines blur in pursuit of something greater. Take the mathematician's role. Primes aren't merely numbers, they're the universe's most stubborn digits, resisting division by anything but themselves and one. When they appear in FRB intervals, number theorists see more than coincidence. They recognize a fingerprint of deep structure. Some are exploring modular arithmetic, a branch of math used in cryptography, to test whether the bursts follow hidden algorithms. Others are modeling the sequences as outputs of dynamical systems, chaotic processes that can, under precise conditions, spit out orderly primes. It's like studying how a dripping faucet might, against all odds, start counting in Fibonacci. The implications stretch beyond astronomy. If natural cosmic processes can generate primes, it could rewrite our understanding of mathematical patterns in nature, from quantum physics to evolutionary biology. Physicists, meanwhile, are pushing the limits of extreme astrophysics. If magnetars or colliding neutron stars are behind the bursts, their magnetic fields and gravitational waves must operate under conditions so extreme they defy laboratory replication. Teams are running plasma simulations on supercomputers, trying to coax virtual stellar corpses into emitting prime-timed pulses. One radical hypothesis suggests quantum vacuum fluctuations near black holes could trigger energy releases at discrete intervals like a cosmic drumhead vibrating at prime harmonics. The challenge: these ideas straddle the line between established physics and speculative theory, requiring equal parts rigor and imagination. Then there's the AI revolution. Sifting through terabytes of radio noise for faint FRB echoes is like searching for a whisper in a hurricane. Machine learning now does in minutes what once took months, with algorithms trained to recognize burst signatures even when buried in interference. But the real breakthrough came when researchers realized these tools could spot something humans might miss: higher-order patterns. One neural network recently flagged a subset of bursts with nested prime intervals, sequences within sequences, hinting at a layered structure that might encode information. Whether that's natural or not, the discovery proves that decoding these signals requires not just human intuition, but machine-aided perception. Linguists and information theorists bring an entirely different lens. By applying techniques developed for deciphering ancient scripts or detecting spam emails, they're testing whether the bursts exhibit properties of symbolic communication, redundancy, syntax, or Zipf's law, a statistical hallmark of human language. While most caution against premature conclusions, the exercise itself is transformative. It forces scientists to articulate what, exactly, would distinguish a natural signal from an artificial one. Is it enough to find primes, or would true design require additional layers of complexity? The debate mirrors SETI early days, when researchers grappled with how to recognize intelligence in a universe full of strange but natural phenomena. This cross-pollination of ideas is yielding unexpected spin-offs. Cryptographers are adapting FRB-inspired prime algorithms to secure quantum networks. Data scientists are borrowing burst detection methods to improve earthquake prediction. Even music theorists have joined the fray, composing works based on FRB rhythms to explore whether mathematical beauty transcends species. The collaboration underscores a profound truth. The universe doesn't parcel its mysteries into neat academic categories. Solving them demands not just expertise, but the willingness to venture into unfamiliar territories, to let a physicist think like a linguist or a mathematician reason like a detective. What's emerging is a new model for scientific inquiry, one as boundaryless as the cosmos itself. The prime-numbered bursts have become a mirror, reflecting not just the enigmas of deep space, but the untapped potential of human curiosity. Whether they're cosmic lighthouses, stellar heartbeats, or something beyond our current frameworks, they've already achieved something remarkable, uniting disparate minds in a shared quest to decode the universe's most tantalizing whispers. Among the countless fast radio bursts detected, one stands out as a Rosetta Stone for astronomers: FRB 121102, the first known repeater. Discovered in 2012, this enigmatic signal didn't just flash and vanish like its counterparts. It kept coming back, pulsing sporadically from a dwarf galaxy 3 billion light-years away. What makes this burst so pivotal isn't just its repetition, it's the extreme environment it calls home. Nestled in a region of frenzied star formation, FRB 121102's host galaxy is a cosmic cauldron, churning out new stars at a rate that dwarfs our Milky Way. This chaotic nursery, brimming with magnetars and supernova remnants, offers the first tangible clue about where repeating bursts might originate. Now compare that to the prime-numbered bursts. While their intervals are mathematically pristine, their host galaxies remain shrouded in mystery. Could they, too, emerge from similarly turbulent neighborhoods? Initial data suggests some overlap. Several prime-numbered repeaters have been traced to galaxies with elevated magnetic fields and intense stellar activity. But here's the twist. FRB 121102's bursts are erratic, arriving at irregular intervals. The prime-numbered signals, by contrast, tick away with the precision of a Swiss watch. This discrepancy forces scientists to ask, are these two phenomena different chapters of the same story, or entirely separate books? The key might lie in the details. FRB 121102's bursts often exhibit scattering, a telltale smear in their signals caused by traversing dense plasma. This suggests the bursts are erupting from deep within a magnetar's magnetosphere or a neutron star's turbulent surroundings. Prime-numbered bursts, however, tend to arrive crisper with less distortion. Could that mean their sources are less embedded in chaotic debris, or perhaps shielded by some unknown mechanism? It's like comparing a shout from inside a hurricane to a voice echoing down a hollow pipe. The difference in clarity hints at fundamentally different engines powering these cosmic signals. Yet for all their contrasts, these bursts share one haunting similarity: persistence. FRB 121102 has been active for over a decade, defying predictions that its source would fade. The prime-numbered repeaters, though newer to the scene, show no signs of stopping either. This longevity rules out one-time cataclysms like colliding neutron stars, pointing instead to objects that can sustain repeated eruptions: magnetars, pulsars with exotic companions, or something even more exotic. The most tantalizing possibility, that FRB 121102 represents the youth of repeating bursts, chaotic and untamed, while the prime-numbered signals are their evolved counterparts, settling into stable, rhythmic patterns over time. Imagine a toddler's erratic footsteps gradually maturing into a soldier's march. If true, studying both could reveal a life cycle of cosmic phenomena we've never before witnessed. Every new detection adds another piece to this puzzle, inching us closer to understanding whether the universe's most mysterious signals are born wild and learn to count, or whether primes have been the rule all along. Fast radio bursts have become one of the most powerful teaching tools in modern science education, not just for what they reveal about the cosmos, but for how they ignite curiosity across disciplines. Picture a high school classroom where students typically groan at abstract algebra problems. Now watch their eyes light up when those same equations become tools to decode pulses from distant galaxies. Educators are discovering that prime-numbered bursts make mathematics tangible in ways textbooks never could. A physics teacher in Sweden recently redesigned her entire curriculum around FRBs, challenging students to calculate signal dispersion rates to estimate cosmic distances. The result, attendance in her advanced courses tripled. What makes these cosmic signals such effective teaching tools is their interdisciplinary magic. A single prime-numbered burst lesson can weave together radio astronomy, number theory, data analysis, and even philosophy. In Australia, students use real CHIME telescope data to hunt for patterns, transforming into junior researchers overnight. One 14-year-old spotted an anomaly in burst timing that later appeared in a published paper, proof that education doesn't just transmit knowledge, it can advance it. Teachers report that framing primes as cosmic fingerprints helps learners grasp their uniqueness far better than rote memorization. Suddenly, numbers aren't just symbols on a page, they're potential messages from the edge of the known universe. Beyond STEM, FRBs are bridging unexpected gaps. Language arts classes analyze how media coverage of the bursts reflects societal attitudes toward science, comparing sensational headlines with peer-reviewed papers. Art students compose music based on burst intervals or create visualizations that make radio waves tactile. Even ethics discussions flourish when students debate humanity's readiness for potential contact with extraterrestrial intelligence. The bursts become a mirror, reflecting how science intersects with culture, creativity, and human values. Universities are taking note. MIT now offers an entire course on FRB astrophysics for undergraduates, while online platforms like Coursera see surging enrollments in citizen science programs analyzing telescope data. Planetariums worldwide have updated shows to feature these mysterious signals, with interactive exhibits letting visitors tune virtual radios to catch simulated bursts. The educational impact stretches beyond classrooms. Podcasts explaining FRBs regularly top science charts, and TikTok astronomers distill complex concepts into viral snippets using prime-numbered bursts as hooks. Perhaps most importantly, these signals teach a meta lesson about the scientific process itself. When students track how theories evolve, from initial confusion over repeating bursts to the current prime interval hypotheses, they witness science as a living, self-correcting endeavor. A teacher in Kenya uses this to combat misinformation, showing how provisional explanations get refined through evidence, unlike static conspiracy theories. The bursts model intellectual humility. Even top astrophysicists admit they're stumped, demonstrating that uncertainty isn't failure, it's the frontier of discovery. The legacy of FRBs in education may outlast any astronomical resolution to their mystery. They've proven that the most effective learning happens when students engage with authentic, unsolved puzzles, not canned experiments with predetermined outcomes. Whether these signals ultimately trace to neutron stars or something more extraordinary, they've already achieved something extraordinary here on Earth, making the next generation feel like active participants in humanity's greatest adventure, the exploration of the unknown. And that's a lesson no textbook could